Hello everyone. Thank you so much for coming. I thank the organizers for giving me this opportunity to present my work. Without wasting any time, let me begin. So on the basis of the number of conserved quantities a system has, a system can be classified as a non-integrable system or an integrable system. So what are non-integrable systems? These are systems which has few conserved quantities, and they are mostly limited to total mass, total momentum, total energy, and so on. Uh, at large times, they are mostly expected to thermalize to a Gibbs state, and they exhibit some very exotic features like chaos, mixing, ergodicity, and so on. Now, if I start with a system in a Gibbs state and I perturb it a little, the system will develop some internal currents within itself, and then it will ultimately tend to thermalize back to the Gibbs state. The study of this thermalization process from a coarse-grained point of view is described by hydrodynamics. So hydrodynamics, it describes the approach from a generic initial condition to the Gibbs state on a coarse-grained level. Now, these hydrodynamical equations are typically mass conservation laws at the coarse-grained level. For example, if I take the example of a 1D fluid, so I have the mass conservation equation, and I also have the usual Navier-Stokes. I want to focus your attention to this part, the double derivative with respect to position. So this term is typically the dissipation term. In normal fluids, it's the viscous dissipation. You will see another sort of dissipation, which we will study for integrable systems. So so if I want to extend the ideas of thermalization and the hydrodynamics to integral systems, so first of all, the question that we should ask, by the way, these are systems with extensive number of conserved quantities. So first thing we should ask is that, are these systems even experimentally realizable? The answer is yes. So there have been experiments which were conducted and show that there are systems which are integrable. Now, do these systems even thermalize? Or if they thermalize, in what sense do they thermalize? So there have been studies performed on various quantum systems, integrable quantum systems, and they observe a generalized version of a Gibbs ensemble. And so we can generalize the ideas of the Gibbs ensemble and hydrodynamics to the case of integrable systems, where these capital Q i's are the conserved quantities in the system, beta i's are the Lagrange parameters, or also we can call them the chemical potentials. And these equations are, this Q is basically the conserved density, and J i's are the currents. So mostly the studies on experiments are focused on quantum systems. Classically, we can study the aspects of generalized hydrodynamics by a very simple system, which are hardware systems. So what are hardware systems? So hardwares are typically very finite size segments that interact with one another through a hardcore repulsive potential. And why is the finite size important? So let's take the example of hardpoint particles. So we can study the hydrodynamics from a perspective of velocity tracers as well. So when we, let's say in the first case, the hardpoint particles, they collide and they exchange their momenta and they go in separate directions. But I can also study this problem from a quasi-particle point of view, where I follow a particle with a given velocity. So when I consider these two aspects, if the particles are identical, there is no difference from a statistical point of view that between a group of interacting particles and a group of non-interacting particles. But when I consider hard rods, then I see a difference. If I follow a quasi-particle hard rod here, in this case, whenever there is a collision, the trajectories, the initial trajectory and the final trajectory, will have a scattering shift. Okay, so there is the dynamics actually, so hard rods then represent a very simple interacting integrable system where the ideas of generalized Gibbs ensemble and generalized hydrodynamics can be studied very easily. So let's go to the formulation. So normally the hydrodynamics is written in terms of phase space densities, which are defined in this way, where the angular brackets denote averages with respect to the initial conditions. Mostly you can average with respect to initial positions, initial velocities, or both, and both. So an Euler scale, by Euler scale, I mean that on a large length scale and a large time scale, the generalized hydrodynamic equation for hard rods can be written in this way. When I include the Navier-Stokes corrections, they assume this form, where the different quantities are described here. Here, rho is the mass density, u is the average velocity of the hard rod fluid, v effective is the effective velocity with which a quasi-particle hard rod moves, And this n, if you look closely, there is a single derivative term inside, which if I put it back to the Navier-Stokes GHD, it gives us a dissipation term. Now, the solution of the Euler GHD is very easy to compute, but the solution of the Navier-Stokes GHD is difficult. So we approach this problem from a microscopic point of view and see if there is any limit that we can take that from going from a microscopic solution to a hydrodynamic solution. And this we do by the following mapping. So if I consider two hard rods, the centers of two hard rods can't come closer than the rod length A. So, which means that in hard rod system, there is a lot of inaccessible space. The first thing is that I want to remove this inaccessible space so that I can go from a hard rod configuration to a point particle configuration. And as I already told you, if I consider point particles, I can effectively treat them as a non-interacting particles. So studying the dynamics of hard rods from a point particle point of view becomes very easy. So in the case, when I want to map the study of hard rods to the point particle picture, I can relate the phase space density to the point particle phase space density in the following way. Here, PIs are related to the probability of finding the ith particle at some position x with velocity v at time t. So how I can understand it? So let's say I have ith particle at position x. I minus 1 particles will be to the left of x, and n minus I particles will be to the right of x. So this g less than and 1 minus g less than represent the respective probabilities. And and all these quantities are calculated in the point particle picture, which is very simple to calculate in a non-interacting system. Okay. So the results are, so for generic initial conditions, we can see that the macroscopic solution obtained in that way like matches with the numeric solution very well. The circles represent the results from numerics, and we can also do it check the use the macroscopic solution for position annealed and position quench initial conditions. Position annealed is where the initial positions have no fluctuations. Position annealed is where there are fluctuations in both the initial positions and the initial velocities. By the way, these conserved densities are defined in this following way, where alpha equal to 0 corresponds to mass density, shown in this figure. Alpha equal to 1 corresponds to momentum density. Alpha equal to 2 corresponds to the energy density. So with this formulation, we can study the dynamics of hard rods in two different initial conditions. Let's take the first example. So what is this system? We have the red rods. They represent rods which I call background rods. So the velocities are drawn from a Maxwellian distribution, which is a Gaussian distribution. And at the origin, I place a rod, tracer rod, which I give a fixed velocity, which is V0. Okay. Now I want to study the density or the distribution of the position of this tracer rod. How I do it? I know that it will collide with one, so it has its own inherent dynamics, which is given by V0 t. And due to the collisions with the other rods, it jumps. Right collisions will make it jump towards the right, and left collisions will make it jump towards the left. So all I need is to compute the distribution of these two quantities, which is very simple in the point particle picture. And just for show, I have shown you this expression for finite n, and it matches very well with numerics. So in the case of large n, we get a Gaussian distribution. And since annealed case has more fluctuations, we expect that the variance in the annealed case is greater than the variance in the quenched case, and that we observe through numerics as well. So finally, I will consider the case of a domain wall. So what is a domain wall? It is a case of a partitioning protocol, where at the origin, I place a wall. On the left side, I give all these hard rods a fixed velocity, which is equal to V0. And on the right, I have my background rods, which have velocities drawn from a Gaussian distribution. And at time t equal to 0, I let it evolve. So similar to the case, how I find the equation of motion for the tracer rod, I can find the corresponding equations of motion for special and background rods. Here, there are three terms because the background rods suffer collisions with background rods as well as special rods, but special rods only collide with background rods. So here we see that the mass density. The important point is that if you look closely, if I zoom at the shock, you see that this dashed lines are representing Euler solutions. So, and the numerics show that there is a spread, and it is explained very well using microscopics. Why is this spread? This is because of the double derivative term, which I already showed you. This is because of the Navier-Stokes corrections. And the same can be observed for the case of background rods as well. And our macroscopic solution explains it very clearly. If I want to see if that's a diffusive spread or not, I can just see for the macroscopic solution that they are indeed a diffusive spread because the scale is root over t. Okay. Now the question is that can I obtain the same results using a numerical solution of Navier-Stokes? So we did the bare minimum. We used finite difference methods, and we saw that both numerical solution and the microscopic solution matches very well with the results obtained from numerics, and but it doesn't match very much with the Euler solution. Okay, so then we actually tried to take a thermodynamic limit in some way so that we can solve the GSD equations. We are able to find the Euler solution when we take the thermodynamic limit. But for finer and finer structures, we have to approximate this exponential by higher order terms. For large but finite n, we obtain this solution, which actually matches very well with the numerics. And this will be explained better way by Indranil in his talk on Monday. So I conclude my talk by saying that it will be very interesting to study the space-time correlation functions from this microscopic point of view. I am also studying a case where I break the integrability by introducing a backscattering, and more insights on the correlation functions will be given by Indranil and Seema in their talks respectively. So thank you.
Questions? In the beginning, you said that the double derivative term is not because of the usual viscous dissipation, although it is dissipating. Can you comment on what's the microscopic origin of the dissipation?
Okay, so the dissipation, thank you for the question. So dissipation is because of the fluctuations in the initial conditions. So this is a different kind of dissipation. If you see clearly, so in the case of a tracer rod, so if I start with some particle at the origin, it will move with some velocity v naught. And at a later time, its velocity should have been v naught if it was not suffering any scattering shifts, right? But due to the collisions with the other rods, it has a spread. So this spread is somehow connected to the fluctuations in initial conditions, which bring about variable scattering shifts, and then it leads to this dissipation.
Okay. So thank you, Mrina.